everyone. Welcome to our first series of BioEMTalks. And my name is Xia. I'm welcoming you from Department of Embryology, Carnegie Institution for Science, Baltimore, Maryland. And I'm very happy to tell everyone that we have overwhelming registration from 12 different countries and for more than 120 people coming to join this BioEMTalk. This is much more than we had anticipated when we started this talk series. Okay, so this first time that we are doing this talk and also using the virtual space designed by GatherTown. And so if you have any technical difficulty, just bear with us. And while we have people at the welcome booth in GatherTown to help you, we also have an IT person here also helping us to ease out the trouble here. So I just want to go through quickly our today's program and how we plan to run this. Okay, so we're going to start the talks in webinar format. So attendees are automatically muted unless we give you the mic to speak for asking questions. So each speaker had just 30 minutes time. So from 10 to 10:30 is Bruno Humbel, and 10:30 to 11 is Christina Mikeva, and 11 to 11:30 is Doug King. And everything will happen right in here. You don't need to go anywhere, okay? And after this ends, we will have live chat that's set up in GatherTown. Of course, it's a very relaxed. I do want you to have time to go take a drink of water, or if you want to have some snacks and things. And so the live chat has 3 different sessions. It's 20 minutes per session in different rooms in BioEMTown. Okay, if you have 2 around, you will see these rooms are on the right-hand side of the BioEMTown Square. Okay, and we have 3 sessions. And the reason we designed that is because we want to make sure the live chat is not going to overwhelm the system. So we ask people not to have more than 25 people per live chat room, because some people's equipment may not be able to get very good video. And we also don't want the system just be overloaded. So please go around to different rooms and at different time to joining the speakers. And you also have opportunity to go through the vendor booths and just walk around to meet your friends and then chat with them. And through the guidebook that you have already learned that you have various ways to locate your friends and chat with them and go to private space. And then there's also a scavenger hunt in the BioEMTown. You will see the vendors, the logos hidden in different objects. And so when you do the sign up sheet, that they're going to ask you, where did you find the logos? Okay, so before I give the speaker the mic to Bruno, I want to thank all the people who helped me to organize this meeting. So my co-organizers they will all be identified in GatherTown. So if you have any trouble, any comment, any suggestions, please do tell us. And we have people at the welcome booth also help you to guide you through if you have any problem with navigation. I also want to give special thanks to folks at the embryology department, the IT people, Sean and Jeremy and Ed helped me to host this webinar. And Jeremy is actually here helping us to deal with any technical problems. And finally, I want to thank the vendors and for their support in order for us to run this BioEMTalk free for everyone to participate. And I hope you enjoy today's talk and then come to see us again, come to join us again in the following 3 Fridays. Now, Bruno, you can start sharing. I'm going to start sharing my screen. And I'm not going to bother to introduce Bruno because I think his credential is just going to be too long for me to remember everything. So Bruno, just go ahead, introduce yourself, and you will also have opportunity to chat with people and then tell them I know you've been traveling, you've been to all kinds of places. Yeah, just go ahead, take the mic.
Okay, Ruching, thank you very much for inviting me to have the first talk of your adventure. I mean, it's really great what you put up, and I'm completely surprised with everything what I see. I mean, I remember your message in the beginning of this week when I was completely surprised. When? Now? It's already now? Oh shit, I didn't prepare my slides. Okay, and the next thing is, if you say about internationality, I mean, as you have seen, if you look on the list from Ruching, I'm on top left corner. I'm from Switzerland, but I made station in Germany, a very long stay in Holland, and finally ended up here on this most beautiful island, Okinawa, which belongs to Japan. Okay, after this should be a more informal seminar. I decided to show you what keeps me busy for a couple of years, and actually what keeps me very busy nowadays. And this is a volume microscopy, and I try to sum up what kind of different volume microscopy methods exist. I mean, we have the serial sections, which is probably the first at all that has been done. And then since the probably beginning of the 90s, we have transmission electron microscopy tomography. A little later, STEM tomography came up. And then you are really lucky afterwards, you will hear Christina, the inventor, or she laid the base for the ray tomography. And further, we have those modern instruments for cutting in the scanning microscope, either with a diamond or with an ion beam, which is FIB-SEM tomography or serial block phase tomography. Okay, let's start with serial section. I think the paper that impressed me most is this one from White. As you see, it's a paper with 340 pages, so it's a complete book. And this was in the group of Sidney Brenner, who was the first president of our university here in Okinawa. And as you see, they were making a 3D model of the nervous system of C. elegans. It's 302 neurons, 5,000 chemical synapses. And to get this done, they were analyzing more than 8,000 photographs. So you can imagine that huge work. I didn't find out how many years they were spending on it. But anyhow, if you look at this publication, it's amazing. Now for tomography, for transmission electron microscopy tomography, we are doing pretty much the same as you undergo when you have to go to the hospital for X-ray tomography or for NMR tomography, meaning that pictures of you and here of the sample are taken at different angles, as you see here with indicated with these images. And then in silico, here are the images at the 0 degree, -60, +60. So this is also old work done at Utrecht University. And then with this in silico, you back project those images into the 3D space. And then you can cut individual sections also in silico and model the 3D structure of your cell of interest or your object of interest. And also here you can do real big stuff like imaging a whole cell. So this is work done, initiated by Brett Marsh, first at Boulder in Colorado, later in Brisbane. Yeah, Brisbane is correct, in Australia, where he was reconstructing serial thick sections. Each section, he did temp tomography and then put them all together to reconstruct such a nice cell. At the time, we were a little bit smaller in size. We were looking at the Caveoli network, first in cells, in endothelial cells. So the first thing what we realized is that Caveoli is a big network. And then, of course, we were curious if they connect from the outside to the inside. And as you see here, we have one cluster, let's say the purple one, that it's from the outside, and the yellow one is from the inside, but we didn't find a connection between these two networks. So probably for the transport, the vesicle will then pinch off from the outside network and then join the inside network. But so far, we don't have that information. So next is Cryo-STEM Tomography. I mean, STEM tomography exists longer. So STEM tomography on thick section was also somehow started at Utrecht University and then very much propagated by Paul Walter in Ulm. And then the amazing thing was that Sharon Wolf was then starting to do STEM tomography in cryo, which everybody thought this will not be possible because the intense electron beam will boil your sample away. But she showed that STEM tomography gives her the opportunity to 3D analyze the area of interest, the area of the cell which is really of interest. I mean, with ordinary tomography, you see the leading lamella, you see the actin skeleton, you see all kinds of proteins that are in leading lamella or in thin extensions. But the organelles that you would be interested in, like mitochondria, she made a wonderful paper on calcium deposits in mitochondria. That you cannot see with TEM tomography, but you can see it with STEM, because STEM can go up to, wait a minute, I have to fix my pen. Okay, STEM tomography can go up to 1 micrometer thickness. In usual cells, you have here above the nucleus, you have 3 to 5 or something like that micrometer. Okay. So that's what she shows here, so, or what actually Paul Walter showed for the advantage of STEM. If you have TEM, you know, when you tilt, at a certain moment you tilt out of focus. That's what he shows here on this grid. And whereas if you have a very thin beam for STEM tomography, then you have a much further depth in focus. So you have not only a larger penetration depth, but you have also a larger depth of focus. And this is what is one of the successes for STEM tomography. Okay, let's continue to array tomography. As I said, the fine details you will be able to hear from Christina herself. I was very lucky to get, when I was in Lausanne, to get Irina Kolotuev to the lab, who was also doing a lot in array tomography. That's what you see over here. So this would be a single section tomography, the way the group, or White and Sidney Brenner, were doing the neural network of C. elegans. That is, you cut many sections, take them on a whole grid, and then you hope that you keep the right order of those grids. You hope that no film will break, you will not lose the grids and so forth. So it's really tedious work. If you go for array tomography, you will put the section on a support. You can use either silicon or ITO-coated glass cover slips or slides. And as you can imagine here, the sections are far more stable, and you can also put many more sections on those supports. And here you see Irina's comparison on a glass slide, on a silicon wafer, and this would be what you can get on a EM grid. That's this grid over here in the right dimension towards the silicon wafer. Okay, so just in short, the process, you do the sectioning, you align the section, and then she developed this knife together with Helmut Knaggi. And then you drain the water slowly. You still have a little water layer on your silicon disc. You can do the fine adjustment, and then you let it dry. And now you can do several things. You can do immunolabel, like Christina will tell you for sure. And afterwards, you can go to the electron microscope, the scanning microscope, to get the images in the scanning microscope. And as you see, it has also another advantage what Irina developed. So if you have ribbons like you see over here, you don't need to go from one section to the other on the whole ribbon to find your area of interest, but you just cross over here and decide here it's not, here it's not, here it's not, and here it comes. And then afterwards, if you have identified, let's say over here, if you have identified the zone where you're interested in, then you go to the left and the right of the section and you gather the information you need for the 3D. And there is also this machine developed at Harvard by Jeff Lichtman. It's now called AtomTom, and I think it's still RMC Buckler you can buy it from. This is a conveyor belt that goes into the water of your boat of the diamond knife and picks the section up as they come off the knife edge. And with this you can make, I don't know, millions, maybe not, but a few thousand of sections that are on this tape. And then again, you can analyze it in SEM. Another quite genius method was developed by Thomas Templier at the ETH in Zurich. He made a dummy block of epoxy resin that contains, as you see over here, two fluorescent beads, a green and a red one, and it contains also magnetic particles. And that he puts onto the EPON block of the sample you're really interested in. That's over here. And now we can randomly cut the sections and can gather them with the magnet over here. So he can center them and let them sink onto, again, a wafer. And for him, it doesn't matter what sequence of the sections are, because he can define the sequence of the sections with some algorithm identifying the pattern you get on the section with these fluorescent beads. It really looks very fascinating, and I was able, thanks to Erin Tranfield, to hear a talk of him. Now, some simple approaches we did together with Heinz Schwarz from Max Planck in Tübingen. So he was labeling lower accrual sections of Trypanosoma brucei with antibodies against the variable surface protein and an antibody against the under the membrane lying tubulin skeleton. And then he came with the sections and the images to me. We were aligning the images onto the light micrographs onto the electron micrograph, and from there we then could choose the cells we were interested in. So this collaboration expanded with Christian Wurm at Max Planck in Göttingen at that time, and he was doing STET imaging for us. So that's how you see. So with the STET, we got a real beautiful resolution of our fluorescence. So in red, we have the variable surface protein, which is of course on the surface, but it's also lining out the flagellar pocket of the trypanosomes. And underneath, we have the tubulin skeleton. And of course, we have the arrangement of the tubulins in the flagella. And here we have then the electron micrographs taken in our microscope with different detectors. So that was really nice. So you could choose the detector which gave you the best image. I think here probably this detector was the nicest one. You see here very nicely the tubular filaments also here in the flagella. Actually, what I didn't say, we did a quadruple label. We also used gold particles, bigger ones for tubulin and the smaller ones for the variable surface protein, just to show that the technology works. Okay, going further, I got a request from the university in Zurich, from the veterinary school. They were interested to show in electron micrographs that they can find this viral protein. They wanted to express this viral protein in cells and use it in some kind for vaccinations. So actually also for transfer from the lactating mouse in that case, so that the virus particles are transferred to the kids. And to show this, they were doing immunogold labeling. As you see here, I enhanced the gold particles with these yellow dots. And we know now all these here, even here out, this is viral protein. It almost gathers in a crystalline pattern. But if you look at the label, it's seriously poor. And you don't know if this is label, if this is background, because it doesn't really get above background. If you look at the fluorescence image, however, it's completely clear. You have a very intense label. And so this brought us to the idea, oh, wait a minute, maybe I should first give you one of the reasons why the label could be poor with gold, because gold as a colloidal particle has a charge, and the gold particles have a negative charge, and the bigger the particle are, the stronger is the repulsion force between those particles. That's one thing. And another observation I made with tobacco mosaic virus, with measles viruses, is that compared to the primary antibody, you have very, very poor decoration with the gold antibodies, especially with the measles virus. I was able in negative staining to see the virus, to see the primary antibodies, those covering, like those brushes you use to clean your reaction tubes. But if you put then a gold label on top of it, you have every few kilometers, you had one little black spot. So there is something probably also that the nucleic acid those viruses contain, that their negative charge is too high. Anyhow, we came then with the idea, and that's a thing I really would love to follow up here at OIST, is to use the fluorescence in combination with super resolution light microscopy as the label instead of a gold label. That's what you see over here. Okay, I just added this picture of earlier experiment to show you. Everybody says that if you use section, let's say a section approach for volume microscopy, you can always revisit if you are interested in the area. And this SEM image should show you that this revisiting might be a little bit limited by the beam damage you're doing. So it's not as easy as it is usually stated. Okay, now we come to one of those wasting methods. So this is the serial block phase SEM. With a diamond knife, as we see here, you cut off a section. Usually you can do 50 microns. We at the moment do 50 microns, but there are claims that you could go down to 20. We didn't try yet. So anyhow, that's about the set resolution you can get, 50 to maybe down to 20 microns. But it has the advantage you can have quite large surfaces. So if the diamond you cut, and then afterwards with the electron beam you take an image and you stack all the images to get the 3D volume, like you see here on those pictures I stole from the website of Katan. So where I have more experience is with focused ion beam tomography. Instead of the real diamond knife, we are using a gallium ion beam to cut. So with the gallium ion beam, we can remove thinner layers. I mean, I usually do something like 10 nanometer, 5 nanometer is possible, and 3 nanometers are claimed in the literature. So we remove a thin layer, and then what we do is we tilt the sample in normal to the electron beam and go closer to the pole piece so that we can have a higher resolution image. And then we take the image, and then again we go down to the position for the gallium ion beam to cut, and then come back to the electron beam, and so forth, getting this way our 3D data. Yeah, here is tomogram recently, it was last year, and actually here maybe I showed the image already. Here, lockdown on Okinawa was really beneficial because this modeling took a really long time, and thanks to sitting at home, not knowing what else to do, I was able to model this, and it's how Leptospira, this is a Spirochaeta bacteria which is in standing waters, like we also have here in Okinawa, and it's a pathogen that can cross your skin, go into your body, and cause damage in different organs. So we were studying how they cross the epithelial layer. And as you see here, we have two different types. We have Biflexa, which is Leptospirum that cannot cross. And we have Interrogans, that's the one which can cross. And obviously they are signaling to break the tight junctions and adherent junctions and so forth. And then can slowly crawl on the surface, like you have seen in the movie. They crawl then on the surface in between the cells into your body. Another project we are working on, again with our local university, with the University of the Ryukyus, and this is on diatoms. So Atsuko Tanaka is interested in the chloroplast, and now I missed to show you. I have maybe to go back. Let me go back. How can I go back? Okay, let's go back. Here, she's interested in this pyrenoid, and this pyrenoid structure is dependent on the CO2 concentration, because these diatoms are very helpful in taking up CO2. I mean, they produce, of course, oxygen, and then they can even eliminate more or less CO2 from our atmospheric surface, because when they die, they will sink on the ground of the ocean. And this could be one of the methods to help our CO2 problem. And just to make you a comparison, here we have a FIB-SEM image. It's a little bit cheated because this sample is prepared by high pressure freezing and freeze substitution. And then compared to the serial block phase image, as you see here, we still have problems with resolution and charging. And I guess one of the problems is because I don't like to use those specific serial block phase imaging preparation protocols, because you use such a lot of osmium that you destroy most of the intracellular structures you keep over the membranes. And I'm really interested from my past, which started in the lab of Martin Müller, who didn't allow us to do any chemical fixation at the time when I did my PhD. I still have this philosophy: we should keep the structure as native as possible. So that's a struggle I will probably fight for the next couple of years, at least as long as I'm here at OIST. And maybe going directly to this summary slide. So if you go to serial sections, we can get, let's say, XY resolution in the range of 1 nanometer. We can section thin, like about 50 nanometer. Usually we are going to 70 to 100. But you can overview millimeters. You can make millimeters sections. So yeah, I mean, not too many, but at least 2 millimeters we can put on an EM grid. For tomography, the resolution is slightly compromised in XY. It's something like 2 nanometer, probably 4 or 5 in Z. The section thickness can be like 500 nanometer for tomography. and you can image surfaces so in the range of micrometers. STEM tomography, similar resolution, but the section thickness can be thicker, can be at least twice 1 micron, but there were also claims of thicker sections. I think FEI once claimed that they can do cryo imaging up to 3 microns. Unfortunately, I've never seen those data. With this, again, you are in the range of micrometers surface, what you can image at the time. And array tomography, it's probably very similar like serial sections. You lose some of the resolution because you're not looking at it in a TEM, but in a scanning microscope, where you get the problems with the penetration depth of the electrons and the excitation, because the beam is broadening when it goes into the section. So the resolution in XY is a little less. And the same is true for serial block phase and FIB-SEM, or for FIB-SEM or serial block phase scanning microscopy. Here for FIB-SEM, we are something like 5 and 30 nanometers. Sorry, that's serial block phase. Now I'm starting to mess up. No, this is the area you can image, and with serial block phase, you can go up to 200 micrometer in square, or maybe even a little bit thicker, and the section thickness would be about 50 nanometer. I hope my last words didn't confuse you too much. With this, I would like to thank all the people so far involved. I mean, as I started with Irina, Celine, these were the people at the Lausanne University who were starting the correlative work and array tomography. Then the collaboration I have now with Claudia Thoma and Nobuhiko Okura on the leptospira, with Atsuko on diatom. Gosha Hall in the lab was helping a lot. Now I have fortunately another person who can join, Ai Takahashi, who will be helping out in future, very dedicated person. The virus work together with Elisabeth and Anita and Andrea. Utrecht, this was the Caveoli work. And with Heinz, Daniel Jans, and Christian Wurm, we did the Trypanosoma. And all the time, I had the support of many people from FEI company helping me with special edition of their correlative software. The nice hint about tilting changes in the FIB came from Chengge Zhao. And here you see some of the organization that were financing us, BioEMTalks project of Japan, Swiss National Science Foundation, European Network of Excellence, and different universities involved. And with this, I hope I didn't exceed too much. I would like to thank you very much for your attention, and I guess afterwards in the lobby room we can talk about some questions you're having. Thank you.